In this exercise, we are asked to find the, well, we have three different questions, and they are fairly unrelated. So let's get started with the first one here. Here we have a number of independent variables, x1, x2, infinitely numbered many. They're all normally distributed with mean 0, variance 4, and we are asked, well, j here is the smallest value of little j, such that this xj random variable is larger than 4, and we're asked, it's basically to find the expectation of j in terms of the standard normal CDF. Now this question takes a little bit of time to wrap your head around to understand what it actually means. So let us start by just writing down xj larger than 4 and figure out what it actually means in this context. Okay, so xj larger than 4, and j here, this means any x really in this order that we have here up here of the x1s. Let me just move this down again here. x1, x2, we have infinitely many x's. Okay, and so what does it mean that xj is larger than 4? We're given the information that x is, well, any x, xj, is distributed normal, 0, 4. So if you draw the PDF of this random variable, this is the PDF, xj looks something like this, and the standard deviation is the square of 4, so it should be, it is 2, and that's minus 2. And what we are asked for to find here, this is an event where xj is larger than 4. So what we're looking for is a is when the random variable here exceeds this region. So we want this region. We're looking for the probability of that region there. All right. So that's, now we have a better understanding of what it means for xj to be larger than 4. So let's write down that event. And actually, one other thing before we proceed doing that is that because the question is asking us for writing down the this expectation in terms of the standard CDF, let us transform this this PDF here into a standardized version. So what does a standardized version mean? A standardized version means is that any random variable normal can be written down as the following. This is the scale transformation. So the mean of xj plus, so scaling factor xj, standard deviation of it, and so just normal algebra here, nothing fancy. We're writing down, oops, it should be xj z. All right, and but we know that the mean is 0, and we also know that the standard deviation is 2. So hence we have the following relationship between any xj, and you might want to call this zj if you want. to be consistent. So let us just visualize the PDF of well, I can just write down with phi, right? That's how we denote the standard standard normalized z. So here's 0. Now we know that this should be 1, right? Let's just write down what it means. Zj is normally distributed 0, 1. That is, per definition, what we mean by the standardized xj. Okay? And so, finding the same event here, what does that mean? Well, in this setting, let me do the following, and let me also write down what we know. What sigma here, the standard deviation is just 2, so xj divided by 2. So that is, anytime we see this event, it means that it's equal to zj. So what does it mean now to have the following events here? Well, it would just mean that we're looking for 2 standard deviations away here, and looking for this region. So that this region here is exactly the same event as this region here, just in a transformed scale. And so let us now proceed by writing down this probability of this event happening. Okay, xj larger than 4. Now we're going to write this down in a format where we can mimic or have this equivalence satisfied. So we're going to, instead of dividing by 4 or any other number, we're going to divide this by 2. Right? We're dividing by 2 in order to get this inequality here, and now we can see that this is the standardized version. So we just write z larger than 2, and we are also going to write down the complement instead to flip the inequality in order to say, well, this is the definition of the CDF of z evaluated at 2. Okay, so in all this, I'm going to just denote as little p here. So this little p is the probability of xj being larger than 4. Okay, so let's move on to think about what it means to all right, and you might also ask, where is this, why is this 2 here equal to this event here at 4? And that is a good question, and basically that we realize by looking at this event, z being less than 2, is the same as, let me write down the following. So before we divide by 2 here, I'm going to just write it down to make it explicit to p xj larger than 4. Okay. Before we made the division, we see that this event is basically that event here. Okay, let's move on. Now we are asked in the final step to find the expectation of j. And what does j really denote here? So let's write it down. Expectation of j is really a geometric distribution, because we're asked to find the event where the index of the first xj exceeding 4. So it could be any of these random variables here occurring independently, and any of them can exceed 4 at any point with probability defined here by this p here. Okay, so that we'll write down as the sum j going overall, starting at 1, looking for the first success, j times the probability of j equaling little j. Okay, and this term is the PMF of the first success, which we write down as being 1 minus p j minus 1, little j minus 1, and the success term 1 for j in the set of 1 up to any term, any number approaching infinity. Yeah, and so that expectation, I'm not going to do the derivation here, but we know that the expectation of the geometric, the first success is the expectation of the geometric plus 1, because we're adding the first success term. And that is simply p divided by 1, which is, let me just move this down here to make a little bit more space, 1 divided, and we said that p is this term here, which gives us the desired expectation. Okay, in the second question, we are asked to define f and g in the following way. We're letting x be a random variable with the PDF of f, and we're asked to find the expected value of the following ratio. And here we start by simply writing down the expectation of r as it is, and we use Lotus here. This inequality, this equality, sorry, goes over the support of x for the transformation. Remember that r here is defined as the random variable x inserted into the function, the PDFG, and PDFG little x now. So it's a transformation and its own PDF times its PDF. Okay, now we see that f of x cancels. Here they cancel. We're left with g of x integrated over x, and since this is a valid PDF, we're given that in the information above, this will sum to 1. In the third and last exercise, here we define the following CDF. It's a continuous and strictly increasing function, and we're letting x have this CDF, and we're going to define w equaling, now we're inserting x into its own CDF, and we're asked to find the mean and the variance of w. All right. So there are two ways to think about this problem. We're going to start with the most obvious one, which we would call the method one. Just use the universality of the uniform Okay. What does it mean? Well, again, we've used this several times in the exercises previously, and we'll be continuing doing that. W is defined as the CDF, x being inserted into CDF, and this is just a standard uniform, so that's distributed as 0, 1, and the expectation of that is the following. I mean, it's a calculation we've done several times, but let me do it again, just to remind ourselves. So it's u times its PDF, like that, and this is square 2, right, and the expectation is half, and the variance of u, just writing down the definition, u squared minus u squared, like that. And we know that this term here, we can insert what we calculated up here, so that will be, and square it like that, and we calculate the following term using Lotus, so inserting u2 and u squared, and do the same calculation as we did here above, but we start with the u squared term, and so that will be, oops, let's do the same color, like that, and this amounts to 1/3. And so going back up to this calculation here, we have 1/3 minus 1/4, and that is 12. 4 minus 3, 1, 12. And that is the variance of the uniform. Now, method 2, how would we approach that? So again, thinking about what it means, let's do method 2, and I'll call this a direct way of calculating the CDF. First, let's start with the CDF and see if we can figure out what that term up here means. So start with the CDF. W F of W is the probability of W being less than little w, and the random variable w, we insert the transformation of x w. Well, it doesn't matter if it's equal less than 2 to w, and we solve for x to free that left term up. Take the inverse to get rid of the CDF here, and now we started with the CDF of w, and now we've moved to the CDF of x. Yeah, and that is what x here was inserted into its own CDF. So this final move here, we might want to actually just denote this probability here meaning that it's over the CDF of x, and this move here we started with the CDF of w. So right, this is like that. So taking the inverse, taking the inverse of this function over that function, those just cancel out, and we end up having w. So saying that, let me move this whole expression here just slightly to the left. This expression here, w, well, that must be a uniform, because no other random variable has this structure to it. So that again must be uniform, as I just said. Sorry, 0 and 1, and we would do the same calculations as we did here, but this is just another way of realizing what we're dealing with, and without using the universality of the uniform at all in these calculations. Right? I see that I'm missing parentheses there.